The pulse width modulation can be implemented in the analog domain too. So the structurally you will see that it comprises of a comparator plus and minus like this. You have a triangle high frequency carrier which is a triangle, and you have the low frequency modulating signal like this. The modulating signal and the triangle signal, high frequency triangle signal, are compared to get an output, and that output is the resultant PWM or the pulse width modulated signal. This is the basic concept of the PWM. So there are several applications which people build the PWM circuit in the analog domain itself. Though majority of the application nowadays use the PWM that is generated in the digital domain inside a microcontroller. But let us also have a look at how to generate pulse width modulation using op-amps. Then later on we will also look at how to do pulse width modulation in the digital domain. So first with the op-amps. So let me take an op-amp. First, let me build this triangular carrier. It's a simple op-amp triangle generation. So I take this op-amp. I will have a hysteresis comparator. Minus pin is grounded. VCC and VEE, you have to get the power supply. The plus pin going to give this resistor and a positive feedback resistor so that you get the hysteresis action. So this becomes a hysteresis comparator. So hysteresis comparator. Then the output of the hysteresis comparator is given to an integrator, an op-amp integrator. Op-amp integrator consists of a resistor here connected to the minus terminal. Positive terminal is grounded. You have to not forget this VCC and VEE. And from the minus terminal to the output, the feedback is through a capacitor. So this is an op-amp integrator. You know the operation of an op-amp integrator. So if I give a constant current here, the capacitor will charge with the constant current, and the polarity of the capacitor will depend upon the direction of the current. If the current is flowing, if this is positive and the current flowing in this direction, the capacitor will charge with a plus on this side where I am showing the cursor, with a plus on this side. If this is negative, current is going to flow in this direction and the current will flow in this direction here, and the capacitor will charge with this side positive, with the output side positive. And the output of this I will connect it to this point input to give the oscillation effect. So now this is a positive feedback triangle generator. How this operates is pretty simple. So let me just have two axes here. I will call this one as VA and this one as V0. So VA and V0. Now at some point in time, let me say that VA is negative. So how it is negative? Superposition of this at this point with the other signal is this output voltage at this point. So this point is the superposition of this and this. If this is less than 0, then this will be negative. So let's say this is negative. So when this is negative, this point is negative, current is flowing in this direction, current flows in this direction through this. The output side will be positive. The capacitor will charge in that fashion. So which means the output voltage will increase. Output will nothing but the voltage across the capacitor. And the output voltage will increase like this. So it keeps increasing. And at some point, this would have increased to some value. This is still negative. Superpose at this point, this negative voltage and the positive rising signal. At some point it will cross 0. When it crosses 0, then this will switch. VA will go positive, VA will go positive. And the moment this goes positive, current starts to flow in this direction, the integrator, and the capacitor voltage falls. The capacitor voltage will start falling. So it will start falling till when? Till this has gone negative. Superposition of this positive value of the voltage at this point and the negative value of this one at this point. Some point it would cross 0. So at this point, let us say it crosses 0, starts going downwards, then you will see this again flipping. So let me mark that point, and you will see that it flips, goes negative. The moment it goes negative, again the current direction changes, and you will see the output rising. So in this fashion, continuously you will see a triangle wave getting generated. This RC controls the rate of rise of this triangle wave, because this R here controls the amount of current that is injected, and amount of current will tell you the rate of rise of the voltage here, right? Because the voltage across this is nothing but 1 by C integral of I dt. The value of the I will also give you the rate at which this triangle slope changes. So therefore, by adjusting this resistor, I can do a frequency adjust. So this resistor will give me frequency adjust. Likewise, if I want to adjust the amplitude, of the wave, I can adjust the hysteresis effect, which will affect the superposition value. So the value of this resistance and these resistances will affect the superposition value. So I can use this resistance to give an amplitude adjust to the triangle wave that is getting generated. So in this way, we have a triangle wave that is generated, right? So here you have the triangle wave. So this is a modulating signal coming from elsewhere. Now this two we need to compare. So compare, how do I compare? I can use an op-amp comparator. I can use one more hysteresis comparator. And the output of that will be a PWM, pulse width modulated waveform. We can implement this and then check this out. You can implement it on a breadboard and then check it out. You can also simulate in ngSpice and check it out. Let us go to KiCad and open a new project called PWM project, and then try to enter the schematic of the triangle generator that we just did, and then go on extend it to PWM generation. So as before, let us go and open a new project, and let me call that as PWM. So PWM analog. Save it. So this is created, and I will copy and paste my library files. Let me go in there, copy, let me go to the folder, the previous folder where I had the models and the symbols. I will copy and then bring it in here to PWM analog, and I will paste it here. So this will contain all the blocks and the device libraries that I had created earlier, and I will go to the symbol editor and give the proper paths. So my library is not being shown up here, so I will go to preferences, manage symbol libraries, Go to project specific libraries. Now here I will include my blocks. I'll include that. That is included. Then add one more, my components. I will include my components also. So this should take care of my libraries. Now they are all added here, all these libraries. I am now ready to go to the schematic page. Open the schematic, and we are ready to enter the schematic for the PWM. Let me take the text and then say this is the op-amp based PWM. The pulse width modulator. Pulse width modulator. So place this title here, and let us now call the components. Go to the right side, add symbol, and here let us bring in the components. So from the library, let me take the op-amp. We will need op-amp. We will need two op-amps, one and one more op-amp here. So let me place these two op-amps here. Then I will need resistors, R. I will need 1, 2, 3 resistors. Let me place them. 1, 2, and 3. 3 resistors. I will need a capacitor. Let me pick the capacitor. I have a capacitor. And I need VCC and VEE power supplies. So let me click here and take source. So let me go here and take E source. So this is one E source. I will take again another E source. Place them here to make VCC. Then I will take the 0 reference node. And once again a reference node here. So now we have all the components in place. Let us make the connections. I'll take the wire. I'll connect this here. And then connect the ground here. So that takes care of VCC. Let me give the label VCC, and then I will place it here. And VEE, and I will place it here. Make the connections. Done. So now I have the VCC and VEE available. I need to see that these op-amps are also accordingly connected to VCC and VEE. Let me copy VCC, place them here. So 2 VCCs, and I also need VEE to be copied and pasted here. VEE. Yes. And let me make that connections. So you see that the op-amps have been powered up, plus and minus. And then the other parts of the circuits, let us organize them. Let me rotate and then place it here. Then I will rotate this and place it here. This I need to rotate it and place it in this fashion. Let me mark all this, push it to align like this, and the capacitance, and let me place the capacitance here. This needs to be rotated and placed here. Yeah. So now we have all the components placed appropriately in proper location. Now we will join. Let me move this here. So now let us join all the components with appropriate wire connections, just like what we discussed. And so this forms the hysteresis part. Only thing is that I need to flip the op amp. I need to do a vertical flip of the op amp so that this is taken care of. This should be now a positive feedback. But if I make a flip of the op amp, then I have to reconnect this. Let me again bring that back. I will do a slight adjustment the way I connect it. I will delete these connections and connect it slightly differently so that I don't have to worry about so now I will make the connection of this and then make the connection for the ground here. So the op amp orientation doesn't change, but all else remains same. Continuing, I will connect this and this to this. The integrator is coming up and we have the integrator connected. So this forms our triangle generator. I need to do a closed loop from the output to this point here. So from here I will go up there and connect it here. This will get connected to this point. So let me realign this like this and push this up. So now you have the circuit in place and I need to give the values. For the sources here, I will say plus minus 15. So which means I'll give 15 volts and 15 volts. So which means that VCC is at 15, V is minus 15 with respect to this one because of the polarity here. So this is a plus 15, minus 15, plus 15, minus 15 power supply. Now this also needs to be grounded. So let me make a copy here and paste. And then go to the wires and make this connection. That is done. Now let us give some values. Let me give some values here. 10K And for this one, let me give it as 120K. And then let me give 5K. And then the capacitance as 10 nanofarad. Okay. So this will give you the integrator action. Now all the points are there. Let me also have a tag. I'll call this triangle, TRI. So I will paste it here and make the connection from here to here. Before simulating now, let us place the control statements. Dot control, option, rel equals 0.01, ABS tall equals 0.01, VN tall equals 0.01. I'll use tran 1 microsecond. Let me give a value of around let us say 20 millisecond and UIC. Run, set color background equals white, set background color to white, set color foreground black, set foreground color to black. Plot V of TRI node, the triangle node, and dot NC. So let me left justify and then let me double click, left justify and place it here. So see that voltage of TRI node is the output. So we should see what comes at that. There you are supposed to get a triangle waveform. Let us simulate this and then see. Let me save this, export the netlist to Spice netlist form and as pwm analog.cir. Save, and we can always check the CIR file. You have the CIR file, double click on that. Then you have the analog.cir. So this is the schematic, and then you have the control statements, and it looks into lublocks.lib. This is for the op-amp symbol. So the op-amp library is being referred to. So you can now simulate it by going to the command window. Let me pull a command window, and now here in the command window I'll say ngspice pwm analog.cir. This I execute in ngspice environment. So on executing, you see that the output is 0. The voltage at the output of the triangle is 0. Not to worry, it's expected. I wanted to show you this. See, the output does not, because the voltage across the capacitor is 0, the oscillation does not build up. give an initial condition to the capacitance. So here in the capacitance value, double click, and I will say initial condition equals some 1 volt corresponds to. So this comes in here. So the moment you give the initial conditions, save it, and then I will again export the netlist, spice netlist here. Let us save that, and you will see that here in the .cif file, IC is equal to 1. The initial condition also appears. Now this will make sense. Use initial conditions in the transient analysis. The initial condition values will be used to start the simulation. So now let us execute it again in ngSpice. So let me come out of ngSpice, start afresh, and I will run ngSpice pwmanalog.cir, and I will. So now you see that the waveform comes up, and this is a high frequency triangular carrier. If I zoom in, you will see the triangular waveform going from a plus value to a minus value. Now you see that the frequency can be adjusted, as I said, by adjusting the value of this resistor. So you can go, you can decrease the frequency by increasing the value of R, and the amplitude can be adjusted by adjusting R2. So R3 and R2, if you adjust, we will get the amplitude adjust and the frequency adjust. So let us just have a look at that. So you can calculate the period by clicking at this point. So you will get the X value, and then click at one period away, so you get the X. So this minus this will give you the so this X minus this X will give you the time period. So let us calculate the time period. So I can calculate that by going into Octave. You can go to Octave or MATLAB command window and then find out. So you have, let us say, X equals 0.0069125. That is one value. And then you have X0, which is 0.0689518. So X minus X naught will be 1.747. So this is the time period difference. So TS. And 1 by that one will give you the frequency. So the frequency will be 5.724 10 to the power of 4. So around 57 kilohertz. So now we can alter the value of R3. I will do that. Alter R3 to 10K. Tran 1 microsecond, 20 milliseconds, time period UIC, and you have that. Then you plot voltage of the triangle node. So you will see the Now let us say this is one value of x and this is the other value of x, right? And I can go back to the command window and then say the time difference t equals 0.00642741 minus 0.00639337. So this is the time difference. So you see that the period has increased, which means that the frequency has reduced, and frequency will be frequency is equal to 1 by t, and that is around 29 kilohertz. From 57 kilohertz it has come to 29 kilohertz. So you see that this will give you frequency adjust, and by changing the value of R2 you can get amplitude adjust. I'll just also quickly show that. So let us have a look at the amplitude first. Now the amplitude is around this point 1.221 and this point is minus 1.16. So it's roughly plus or minus 1.2, right? So let us do an adjustment, alter R2 from 120K, I will make it 200K. And again run the simulation 1 microseconds to 20 milliseconds UIC and plot voltage of the triangle node. So you see here the amplitude is around 0.6 plus or minus 0.6. So you get the amplitude adjust by adjusting this value of resistance. So use this for frequency adjust, this for amplitude adjust. You get a triangle. Now that I have the triangle, I can append to this the comparator portion. So we saw the simulation of this triangle generator performed as per what we discussed. Now let us continue and complete this part. We shall include a comparator to do this job of comparison between the modulating signal and the high frequency triangular carrier, so that we get a pulse with modulated waveform. So let us continue the circuit and add one more op-amp to complete the PWM. So I will draw an op-amp here. Don't forget plus 15, minus 15, VCC and VEE. So these are the two terminals, and like here I will give the negative terminal to this triangle which is generated, and I'll have a modulating signal. Let's say we give a sine signal, some modulating signal, and connect it here. This will be the output, which will give the PWM. I'll call this V0, and this V0 I will change to V triangle, VTRI. So VTRI is given here, compared with the modulating signal. The comparator does the job, and then you get high and low here, V0, PWM. So that is one part. And we also saw, while generating the triangle, by adjusting this resistor, we could change the frequency. And by adjusting this resistor, we could change the amplitude. So normally for the triangular carrier, we would like to set it at plus minus 1 volt. 1 volt would be the limit of your triangular carrier, or if it is a sawtooth going from 0 to 1 volt. Either we would like to have 0 to 1 volt or plus minus 1 volt for our triangular carrier. So let us set that peak amplitude to 1 volt. How do we do that? By adjusting this. So these two resistors are the ones which determine the hysteresis window, and the upper trip point and the lower trip point gets decided by these two values. So let me mark this as R1 and I will mark this as R2. So this is the point of interest V plus. So if V plus is equal to 0, if it is going greater than 0, output VA will be high. If this is going less than 0, at 0 minus, this will go to a negative value. It will go and saturate to VEE. So this is the point of interest. And this is one source which we need to superpose, and this is the other source, or this other voltage that we need to superpose to obtain the value here. And let us say that we will obtain the value at this peak. This is what we want it to be 1 volt here at this peak value. At the time corresponding to this value, this is at minus 15 volts or VEE. At this point. So at this point, at this transition point, flipping point, let us write the superposition equation. So this is V naught or V triangle into R2 by R1 plus R2 plus VA was VE into R1 by R1 plus R2 should be equal to 0. So if I take the modulus, if you take it on the other side, take the modulus of VEE, V triangle by modulus of VEE should be equal to R1 by R2. So what does this mean? So let's say this is 15 volts. VEE is minus 15 volts. Plus minus 15 volts is the supply voltage. So let's say I'm setting it at 15 volts VEE modulus, and R1 is 10K. Then if I want V triangle peak amplitude to be 1 volt, that is to be 1 volt, then I know the ratio that R2 should be 150K. So if I set R2 to be 150K and this one as 10K, then I will get a triangle amplitude of 1 volt peak. Okay. So let us now complete the PWM circuit on the schematic and then simulate it in ngSpice, and let us just have a look at the waveforms. So I have opened the schematic where we simulated the triangle waveform generator. So here I will make some changes. The value here, let me set it at 150 like what we discussed, so that V is 15 volts, we have given plus minus 15 volts here, so that we will get output triangle of plus minus 1 volt amplitude. So that is one thing. And next, let me include one more op-amp for comparison. I'll go to add symbol and take an op-amp from the my block. From my blocks, I will take the op-amp symbol and place it here. I will place it here. I will move this around a bit. Let me move this here. I also will need a modulating source. Let me pick a modulating source, V sine. Let me give a sine wave modulating source, V sine. and place it here. I will need a zero reference node here. Then let me draw the wires. I will remove this for now and then I will connect it later. So triangle goes in here direct. The modulating signal goes to the plus terminal. Let me connect that. Yes. And the output is what we will have for the PWM V0. I will also have to give the supplies. I'll copy VCC and paste it here. And I will copy VEE and place it here. And let me connect them. Right. I will take one more label for the output, V0. So this label is for V0. And then this is the triangle, and I will have one for the modulating signal. One more label, M, for modulating signal. And then I will place it here and connect them. So this is the triangle, this is the modulating signal, and this is the output. So we can observe these waveforms. Now for the modulating signal, let me give, because I am expecting the triangle to be up to 1 volt peak, I will make the modulating signal go up to 80% of it, 0.8. And you see that the triangle was having around 57 kilohertz frequency we calculated. I will go 1/10 of that frequency for the modulating signal, let's say 5 kilohertz, so that you will be able to see it in the display without zooming directly. 5 kilohertz sine wave, the modulating signal. The triangle is generated at what you get is approximately 57 kilohertz or something. And then here I need to change this. So 5 kilohertz would work out to be 200 microseconds. I'll make it 200 microseconds. And then what do I want to see? I will want to see the triangle. I would like to see the modulating signal, and I would like to see the output. All these three, right? The triangle, modulating signal, and the output. Let us see all these things. Now this becomes a complete PWM modulator. All things built in there. So now let me save this. Go to export, netlist, spice netlist. I'll export the spice netlist and save it to the pwm analog.cir. So that is saved. So now I can go and pull in the command window. I will exit out of the previous ngSpice environment. Afresh, I will type in ngSpice pwm analog.cir and execute that. So you see here, this is the triangle waveform, and you see that the modulating signal, the blue waveform here, within the triangle waveform, 0.8, we had given the amplitude, and then the modulated signal, PWM, pulse width modulated. So you see the pulse width varying. So when the sine is low, you see the pulse width is small, and the pulse width gradually increases. And you see a large pulse width when the sine is at its peak, and then again starts decreasing. It crosses zero, goes towards the negative, and you see that the negative pulse width is large, or you will see the pulse width going smaller and smaller here for the negative part. So this is a sinusoidal pulse width modulation. Another thing that I want to observe is this. Let me zoom in here. So you see that the triangle. So the triangle again is the getting chopped off because of the resolution. It actually has to go up to 1 as we calculated, plus minus 1, where it's getting chopped off due to the display resolution. And you will see that the sine wave getting compared with the triangle. So at every comparison point, you see that there is a transition. Every comparison point, transition. So like that, what is happening? Every comparison point, you see the transition happening. I will show you that if I increase the resolution of the transient analysis, you will see an improvement in this waveform. This is only a display resolution problem. So let me go. I will just show you that. So let's say that I now do a transient analysis. You see that I had given 1 microsecond as the max step time. I will now reduce that to 0.1 microsecond max step time. Same 200 microseconds UIC. You now execute it. Now I will plot the same V triangle, the modulating signal, and V naught, the output signal. So let us view that. Right? So I will keep this on this side, and then I will mark off. Let me zoom in here at this point. Right? So you see here that I have not done any change in the circuit schematic or the values. It is only the transient analysis display resolution. I have now more number of points, and you see that the triangle is going up to. So this chopping off is merely a display resolution. Keep that in mind whenever you are seeing a waveform which you think that there is some issue. First check your resolution, see that you have sufficient display resolution to plot all the points, otherwise it will skip to the next point. So this way I will allow you to study, change values, and get more insight into this basic, simple analog pulse width modulator, the analog op-amp pulse width modulator. And we also saw before that there are pulse width modulator ICs available like the TL494, which can also be used for generating the pulse width modulation, and everything can still be kept in the analog domain. Later on, we will see that pulse width modulation can be done even in the digital domain with the use of the timers, of general purpose timers of the microcontrollers. Because more and more now all the controls are in the digital domain, and therefore the pulse width modulation also happens in the digital domain. And you should also know how to do pulse width modulation using a microcontroller. We will address that much later.